Hi, my name is Brittany Fink and my partner is Roberto Saenz. Today we will be talking about the analysis of a vehicle's cruise control as it travels through a dynamic environment. Our overview of this presentation is to talk about our motivation, introduction on cruise control, our objectives, and we will not be talking about our appendix, but they are included in our slides. In the world today, most modern vehicles are equipped with a system that simultaneously increases vehicle efficiency, while also reducing driver fatigue. This system uses a combination of sensors and controllers to help the vehicle maintain a present vehicle speed. This dynamic system has become commonly known as cruise control. The motivation behind choosing the analysis of a cruise control system is that it is a system that most people use daily and therefore is often taken for granted by the general public. It is one of the most desirable luxury options on a vehicle to date, and often comes standard on a wide variety of vehicles made and models. The main function of any cruise control system is to maintain a constant preset vehicle speed despite road design and environmental effects on the vehicle. Manufacturers in recent years have advanced this system to maintain a present distance between your vehicle and the vehicle in front of you. This advanced cruise control system also incorporates a braking system of the vehicle for obstacle and collision avoidance. This advanced system has become known as adaptive cruise control and is being offered as standard equipment on many new vehicles coming off of the lot. In more sophisticated vehicles offered, these systems have advanced to incorporate lane assist and self-driving functions. For an introduction to cruise control system, a brief description on the history will be discussed, as well as an overview of the conventional cruise control systems, including the differences in components between earlier mechanical cruise control systems and modern electric cruise control systems. A brief introduction to adaptive cruise control will be covered, along with the overview of the system. Conventional cruise control system primary function is to adjust the throttle input of the vehicle to maintain a preset speed. The vehicle instantaneous speed is consistently changing due to multiple factors while driving. These factors can include dampening force from headwind against the vehicle, change in the grades of incline and declines in the road, as well as a change in direction of the vehicle. Since there is multiple factors that can change the vehicle speed, the cruise control system falls under the class of a MIMO dynamic system. The term MIMO is the abbreviation meaning multiple inputs, multiple outputs. In older vehicles where most vehicle systems are mechanical, the cruise control system worked by a mechanical actuator attached to the throttle cable. Typically, the actuator was vacuum controlled and received an input from the speed sensor. When a change in the speed was apparent, the actuator would engage to adjust throttle position to open or close the butterfly valve accordingly, until the desired speed was achieved once again. Since the actuator physically moved the cable attached to the pedal inside the cab would physically move, which could be problematic to some drivers if it was unsuspected. Newer vehicles have adapted to a drive-by-wire design. In this design, the throttle pedal is no longer connected mechanically to the throttle body. Instead, the throttle pedal is attached to a pedometer or transformer which alters an electrical signal. The signal is interpreted by the vehicle's engine control unit, or ECU, which lets the vehicle know where the desired throttle position should be. When cruise control is activated and engaged to compensate for different speeds, the computer can easily adjust throttle position on the throttle body using an electric motor. Since there is no mechanical connection to the pedal, when the electric cruise control accelerates the vehicle based on the dynamic changes, the desired throttle input can be achieved quickly and more accurately due to the computer inputs. Another benefit of this design is that the pedal does not change position physically, which allows the driver to remove some guesswork when reverting to manual throttle input. This small feature aids in overall driving satisfaction as well as efficiency. In recent years, vehicle systems and controls have become highly sophisticated. Newer vehicles are now offering adaptive cruise control. Adaptive cruise control, or ACC, uses forward-facing cameras and sensors that can detect the distance between vehicles in front of the pilot vehicle. This system not only maintains vehicle speed, It also incorporates the braking system of the vehicle as well. If the forward-facing cameras or sensors detect that it is approaching a vehicle or obstacle too quickly, it will apply the brakes automatically to aid in the avoidance of a collision. Our objective for this assignment is to model the cruise control system and its components such as throttle, speed sensor, and engine management to better understand how the equipment talks to each other. Also to analyze how changes in the environment and road conditions affect the vehicle and how the cruise control system nearly instantaneously adjusts to these changes.
The cruise control system that we designed is designed to accommodate an old Toyota experiencing some strong headwind. From this problem, our base assumptions are a fixed floor, an ideal damper, a lumped mass point, slipless and frictionless system, and it is initially at equilibrium. Now that we know our assumptions, we can set up the system. The force of the engine required is equal to the force of the headwind minus the force of the vehicle plus the damping velocity of the reference speed. After taking the Laplace transfer, we result in a transfer function of 1 over ms plus b. With our transfer function known, we can develop our state space matrices. After rewriting our transfer function in terms of x double dot, after plugging in the variables, we get a matrix of A equals negative B over M, B equals 1 over M, C equals 1, and 0 for D. With our A through D matrices known, we can build the transfer function in Simulink. Now that we have our equations known, we can input our system variables. From the initial block diagram, we need 3 variables: the mass of the vehicle, the dampening coefficient, and the force of the wind gust or step input. The mass is 1,600 kilograms. The dampening coefficient can be calculated using the reference speed of the drag force on the vehicle, and the wind force is also calculated from the drag force on the vehicle. After calculations, we have a dampening coefficient of 21.064 Newton seconds per meter, and a force of wind gust of 253.037 newtons. With our parameters known, we can analyze the open loop step response using MATLAB. The open loop step response is the result of the system if no corrective force acts on the system. Our open loop response indicates a linear increase in velocity reduction. In order to correct this, we must implement a controller. There are 3 controller types we'll be experimenting with: proportional, integral, and differential. Our velocity controller will be a closed loop unity feedback design. In this design, the feedback function T of S is equal to GC of S over 1 plus GC of S. We tested the system with the proportional gains from 1 to 500. This controller achieved a very smooth transition from activation to steady state with no overshoot. However, in none of the gains tested did the vehicle return back to the reference speed of 20 meters per second. It always hovered around 18. We next tested the PI controller. The PI controller adds an integral gain alongside the proportional gain. This controller was best suited for our cruise control system design. It had all the best qualities of the proportional controller. However, the integral gain allowed the system to return back to the reference speed. The integral gain controller, however, also incorporates an overshoot. This wasn't a major issue, however, in fact, it was actually preferred to the design. With the overshoot, it allows the vehicle to go past the reference speed, which would allow the vehicle to upshift if it was necessary before returning back to cruising speed. The last controller we tested is the PID controller. The PID controller yielded us identical results to the PI controller. There was no derivative in initial transfer function, so the implementation of a derivative controller was pointless. Using MATLAB, we also determined our open loop system, which had 1 real pole at negative 0.13. We also plotted the open loop bow diagram to see the phase angle and magnitude of the transfer function as it cycled through. These are the references that we use for our project. Thank you very much for listening to our presentation.